This is the story of what happens after every star in the universe has gone dark, and it does not unfold the way most people picture it. It is not one dramatic explosion on one dramatic night. It is a chain of endings, stretched across timescales so long that the entire current age of the universe barely counts as the opening paragraph. Stick around, because by the end of this video you're going to have a working mental map of essentially everything that happens between right now and the true final dark, starting from the birth of the very first star and ending long after the very last one. And if that kind of deep time storytelling grabs you the way it grabs us, go ahead and hit subscribe before we start, because this channel builds out timelines exactly like this one every single week. Let's begin at the actual beginning, because understanding how something ends usually starts with understanding how it began. For roughly the first 380,000 years after the Big Bang, the universe was too hot for atoms to exist in any stable form at all. Protons and electrons were just careening around as a dense, opaque plasma, a fog so thick that light itself couldn't travel freely through it, scattering off charged particles again and again instead of streaming outward in a straight line. Every direction you might have looked, had there been anyone there at all to look, would have shown you the same blinding, featureless glare, because nothing could travel far enough in a straight line to form any actual image of anything. Then, at a moment cosmologists call recombination, the universe cooled enough for those protons and electrons to finally combine into neutral hydrogen and helium atoms, and space itself turned transparent for the first time in its entire existence. The light released at that exact moment is still out there, and it's actually been measured. Astronomers call it the cosmic microwave background, and its discovery is one of those stories that sounds almost too perfectly coincidental to be real. In the mid-1960s, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were using a sensitive horn antenna, originally built to communicate with early Telstar satellites, to study radio emissions from a supernova remnant. They kept picking up a faint, steady hum of noise, coming from every direction they pointed the antenna, no matter the time of day or the season of the year. For the better part of a year, they assumed it had to be some flaw in their equipment, and they went to genuinely absurd lengths trying to eliminate it, including physically removing a pair of pigeons that had nested inside the antenna horn and cleaning out the mess those pigeons had left behind. The noise stayed exactly the same. Meanwhile, completely unaware of what Penzias and Wilson were dealing with, a team at nearby Princeton University, led by physicist Robert Dicke, was actively trying to build a detector specifically to search for exactly this kind of signal, based on a theoretical prediction that the Big Bang should have left behind a faint, uniform microwave afterglow. Once the two groups connected the dots, they published their findings side by side in 1965, and Penzias and Wilson later received the 1978 Nobel Prize in Physics for what turned out to be one of the most important accidental discoveries in the history of science. That faint hum they'd been trying to get rid of for a year was the actual light of the early universe, stretched and cooled by billions of years of expansion, down to a temperature of about 2.7 degrees above absolute zero, and it's still detectable today, coming from every single direction in the sky, exactly the way Penzias and Wilson first found it, a fossil signal older than every star that has ever existed. There's a detail in that discovery worth sitting with a little longer, because of what it says about how science sometimes actually works. Penzias and Wilson weren't looking for the birth of the universe. They were trying to do careful, ordinary radio astronomy and kept running into an irritating, unexplained problem with their equipment. The most important cosmological discovery of the 20th century arrived disguised as an annoyance, something two working scientists spent the better part of a year actively trying to make go away, before finally realizing it was the discovery itself. What followed recombination wasn't a burst of starlight, though. It was darkness, a genuinely dark stretch of cosmic history astronomers now call the Cosmic Dark Ages, a cooling fog of plain hydrogen and helium drifting through an expanding universe with no stars anywhere to light it up. Imagine a universe that already has space, already has matter, already has the raw ingredients for everything that follows, and simply sits there in the dark for tens of millions of years, waiting, patient in a way that's going to become a familiar theme by the end of this video. That darkness didn't last forever. somewhere in a window that most current research places between about 100 million and 400 million years after the Big Bang, gravity finally won out over that featureless fog. Tiny, almost imperceptible differences in density, regions just slightly denser than their surroundings by fractions of a percent, began pulling in more and more gas, growing over tens of millions of years, into clouds massive enough to collapse under their own weight. Astronomers call this first generation of stars population 3 stars, and they were built from nothing but pure hydrogen and helium, since none of the heavier elements you'd find in a star like our Sun existed yet anywhere in the universe. Those heavier elements, the carbon, the oxygen, the iron, only get made inside stars themselves, forged in the extreme pressures and temperatures of stellar cores, and then scattered outward when those stars eventually die. Which means the very first stars had to be built without any of the shortcuts every later generation of stars, including our own Sun, would get to rely on. That absence of heavier elements mattered enormously, because those elements are what normally help a collapsing gas cloud shed heat efficiently and keep compressing toward the density needed to ignite fusion. Without them, the primordial clouds had to rely on simple hydrogen molecules as their only real coolant, a far less efficient process. And the result is that population 3 stars are theorized to have been unusually, almost absurdly massive, with estimates commonly landing somewhere between 30 and 300 times the mass of our own Sun. Stars that big burn through their fuel violently fast, which is exactly why not a single population 3 star has ever been directly, conclusively observed. They lived hard and died young, on a cosmic scale, long before any telescope humanity has ever built existed to look at them. There's a genuine irony sitting inside that fact worth pointing out. The very first stars, the ones that made every later star, every planet, and every person possible, by seeding the universe with heavier elements for the first time, are also the hardest stars in the entire history of the cosmos to actually find evidence of, precisely because they did their job so quickly and so long ago. Astronomers can describe what these stars were probably like in remarkable mathematical detail: their likely mass range, their likely lifespan, the specific way their explosive deaths would have scattered new elements outward, all without a single confirmed direct observation of one, working entirely from theory, indirect evidence, and educated inference, the same way a detective might reconstruct an entire crime scene from a handful of scattered clues. That said, the hunt for them is very much alive right now. In November of 2025, a research team led by Eli Visbal of the University of Toledo announced what may be the first observed system consistent with all of the major theoretical predictions for what a population 3 star system should look like, based on James Webb Space Telescope observations of a distant galaxy, catalogued as LAP-1b. It's a genuinely recent development, not yet fully confirmed or replicated, but it's the closest astronomers have come to actually seeing the universe's first stars with their own instruments, a target scientists have been chasing for decades. Those first stars did more than just produce the universe's first starlight. Their fierce ultraviolet radiation began ripping electrons off the neutral hydrogen gas that filled all of space, a process called reionization, running from somewhere around 300 to 500 million years after the Big Bang, through roughly 1 billion years after the Big Bang. That process is what officially ended the cosmic dark ages and lit the universe up for good, transforming it from a cooling fog into the structured, star-filled cosmos that would eventually produce galaxies, planets, and everything else. It's worth marking that transition clearly, because it's really the true beginning of the story this entire video is about to tell. Before reionization, there is no stars getting older, no red dwarfs outlasting everything else, no fading, dimming, or decaying of any kind, because there's simply nothing there yet to fade. Everything covered from this point forward, every star, every white dwarf, every black hole, every trillion-year and Google-year figure still to come, only becomes possible once this one process finishes turning a dark, formless universe into one that finally has light sources scattered through it. And it's worth noting that when astronomers look for the oldest surviving stars in our own galaxy today, they find candidates like a dim star catalogued as HD 14283, sometimes nicknamed the Methuselah star in popular science writing, whose measured age comes out to around 14.5 billion years, give or take 800 million years, a range that just barely overlaps with the age of the universe itself. That's a star that appears to have formed almost immediately after the very earliest possible window for star formation, and remarkably, it's still burning today, quietly, somewhere in our own galactic neighborhood, a genuine living fossil from the earliest chapter of everything that exists. There's something worth appreciating about a star like that existing at all. Every red dwarf discussed in this video, the ones expected to keep shining for 10 trillion years into the future, and a star like HD 140283, one of the very first stellar generations to form after the cosmic dark ages ended, belong to entirely different ends of the same timeline, separated by an almost unfathomable stretch of years, and yet both of them are, right now, in this exact moment, doing the same basic thing, quietly fusing hydrogen, somewhere out in the dark, mostly unnoticed. With that beginning firmly established, it's worth pausing to get a sense of scale for just how much is currently out there, because it makes everything that eventually fades away feel a lot more concrete, a lot more real, rather than abstract. Estimates vary considerably depending on the method and the telescope involved, and that variation itself is worth being honest about rather than smoothing over into one tidy number. Older estimates, built on the original Hubble Deep Field images from the 1990s, suggested something like 100 to 200 billion galaxies within the observable universe. Then, in 2016, a team led by Christopher Consolis at the University of Nottingham reanalyzed deep Hubble imagery and concluded the real number is at least 10 times higher, closer to 2 trillion galaxies, because roughly 90% of galaxies out there are simply too faint and too distant for current telescopes to directly see, hidden in plain sight, so to speak, just beyond the reach of even our best instruments. Counting individual stars is even messier than counting galaxies. One commonly repeated figure puts the total at around 10 to the 24th power stars, more than every grain of sand on every beach on Earth combined, a comparison astronomers reach for specifically because it's one of the few things large enough to even begin to compete with that number. A more conservative method, one that integrates star formation rates across the entire history of the universe, rather than just multiplying an average galaxy by a galaxy count, arrives at something closer to 2.21 sextillion stars, a genuinely different number by roughly a factor of 1,000 compared to the sand grain estimate. Our own Milky Way is thought to hold somewhere between 100 and 300 billion stars, depending on which estimate you use, a number so large that even trained astronomers describe it as functionally impossible to picture all at once. And here's a detail worth sitting with for a moment, because it reframes everything that follows in this video. Of every star that has ever formed across the full history of the universe, an estimated 97% or so are thought to still be alive and shining today. Only about 3%, generally the biggest, most massive, and shortest-lived ones, have already died. We are, in other words, still remarkably early in this story, even though 13.8 billion years already feels like an almost incomprehensible amount of time to a single human being with a single, brief lifespan. A life that, measured against any of the numbers in this video, barely registers as an instant at all. It's worth returning to that 97% figure one more time before moving on, because it's easy to let a statistic like that slide past without really registering. Out of every star that will ever exist across the entire stelliferous era, the trillions upon trillions that are still going to form and burn and eventually fade out over the next 100 trillion years, the ones that have already lived and died so far represent barely a rounding error. Almost the entire population of stars this universe will ever produce hasn't even been born yet, waiting somewhere out there in clouds of gas that haven't collapsed yet, in galaxies that haven't finished forming, on a timeline that makes the entire history of human civilization look like less than a passing moment. It also helps to know roughly where the Milky Way itself sits inside all of that, because just one of 2 trillion galaxies still undersells how the universe is actually organized. Galaxies aren't scattered evenly through space, like salt shaken across a table. They clump together into larger structures, and in September of 2014, a team of astronomers led by R. Brent Tully of the University of Hawaii, working with colleagues Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, published a paper in Nature mapping out exactly which larger structure the Milky Way itself belongs to. They named it Laniakea, Hawaiian for immense heaven, and it turned out to span roughly 500 million light-years across, containing something like 100,000 large galaxies with a combined mass of about 100 million billion suns. The way they found its actual boundaries wasn't by mapping where galaxies sit, but by mapping how they move, tracking the motion of thousands of galaxies and discovering that everything inside a certain enormous region flows inward, gravitationally, toward a shared focal point nicknamed the Great Attractor, the same way water in a landscape flows downhill toward the lowest point in a valley. Tully described the discovery about as memorably as anyone could. Finding Laniakea's edges, he said, was a lot like finding out for the first time that your hometown is actually part of a much larger country that borders other nations. And even that immense heaven, 100,000 galaxies strong, is still only a small corner of the full observable universe, which stretches more than 90 billion light-years across in total, meaning even our entire cosmic neighborhood, the one Earth, the Sun, and every star in this video's opening chapters belongs to, is itself a relatively modest structure on the very largest scales anyone has managed to map. Before going any further, it helps to understand how astronomers actually sort all these stars into meaningful categories in the first place, because that classification system is going to keep coming up for the rest of this video. The tool almost every astronomer still uses today is called the Hertzsprung-Russell diagram, and it was developed independently by two people working continents apart in the early 20th century. Danish astronomer Ejnar Hertzsprung, who around 1905 to 1911 began plotting how bright stars actually are against their color, and American astronomer Henry Norris Russell, who by 1913 was doing something remarkably similar, plotting brightness against a star's spectral type using his own parallax measurements. Working independently, without collaborating, the two of them arrived at nearly identical diagrams, and what that diagram revealed was that stars are not scattered randomly across the graph at all. They cluster into distinct, well-defined bands, and which band a star falls into tells you its mass, its age, its composition, and where it sits in its own life cycle, all from two simple measurements. The underlying alphabet soup behind that diagram, the spectral sequence running O, B, A, F, G, K, M, from hottest to coolest, was actually worked out slightly earlier, around 1901, at Harvard College Observatory, and the person most responsible for it barely gets mentioned outside of astronomy history circles. Her name was Annie Jump Cannon, and she joined Harvard in the 1890s to help classify the spectra of stars, eventually becoming so proficient at the work that she could examine several hundred stars an hour, ultimately building out a catalogue covering the spectral types of hundreds of thousands of stars by hand, one photographic plate at a time, in an era long before any kind of automated computing existed to help her. It actually took a couple more decades before anyone fully understood why that OBAFGKM sequence worked the way it did. In the 1920s, Indian physicist Meghnad Saha developed a theory explaining how atoms become ionized at different temperatures, and astronomer Cecilia Payne built directly on Saha's work to demonstrate, conclusively, that the entire spectral sequence was really just a temperature sequence in disguise, hottest to coolest, nothing more mysterious than that. It's worth noting that Payne's broader findings from this same period of work, that stars are made overwhelmingly of hydrogen and helium, rather than resembling Earth's own rocky composition, as many astronomers of the time assumed, were initially met with real skepticism from senior figures in the field, and only later became accepted as one of the foundational results of modern astrophysics, a reminder that even a discovery this fundamental didn't arrive to instant, universal agreement. Our own sun sits comfortably in the G portion of that sequence, informally called a yellow dwarf, even though it's really closer to white. The red dwarfs that are going to matter so much later in this story occupy the cooler, dimmer end of the exact same main sequence band, the M-type stars, quietly outnumbering everything else on the diagram by a wide margin, tucked into the bottom right corner where nobody's eye is naturally drawn first. Now let's bring things much closer to home, because before we get to the death of the last star in the entire universe, there's a far more personal deadline worth knowing about first: the death of our own sun. Right now, the The Sun is what astronomers call a main sequence star, meaning it's in the long, stable stretch of its life, where it's fusing hydrogen into helium in its core, and for a star of its size, that stretch typically lasts somewhere between 8 and 10 billion years total. The Sun is about 4.5 billion years old, putting it a little past the halfway mark of that stable phase, comfortably middle-aged by stellar standards. Not old, not young, just quietly going about the business of turning hydrogen into helium, the same way it has for billions of years already, and will continue to do for billions more. Here's the detail that tends to catch people off guard, though. The Sun doesn't need to die for Earth to become uninhabitable. It just needs to get slightly brighter, and it's already doing exactly that, gradually, all the time, every single year, in a process too slow for anyone alive to ever actually notice happening. The Sun brightens by about 10% every billion years, and within roughly 1 billion years from now, that added heat will be enough to push Earth out of the Sun's habitable zone entirely and start boiling the oceans away, permanently, with nothing left afterward to bring them back. Astrophysicist Don Kurtz of the University of Lancashire summed up the endgame for our planet about as plainly as it can be summed up, telling Reuters that the future of Earth is to die with the Sun boiling up the oceans, while the scorched rock underneath survives. The real deadline for anything living on this planet isn't the Sun's eventual death at all. It's this much sooner heating problem, and 1 billion years from now is the number that actually matters, not 5 billion, a distinction that surprises most people the first time they hear it laid out this plainly. It's a strange thing to realize that the Sun doesn't have to do anything unusual at all, nothing dramatic, nothing out of character, to eventually end life on Earth. It doesn't need to flare, or destabilize, or misbehave in any way. It just needs to keep doing exactly what it's already doing, fusing hydrogen into helium at a slow, steady pace. The same completely ordinary process that's kept every living thing on this planet alive for billions of years, until that same steady process eventually makes the planet too hot to survive on. The mechanism that sustains life and the mechanism that eventually ends it turn out to be the exact same one, just given enough time to run its course. Fast forward past that heating problem, though, and follow the Sun's own life all the way to its natural end, and here's roughly how it plays out from there. Somewhere around 5 to 5.5 billion years from now, the Sun finally exhausts the hydrogen fuel sitting in its core, fuel it has been steadily burning through since before Earth even existed. Once that happens, gravity takes over inside the core, compressing it, heating it further, and igniting a shell of hydrogen fusion in a layer wrapped around that now inert core. That shell-burning phase is what actually turns the Sun into what astronomers call a red giant. And it does 3 things at once. It makes the star dramatically brighter, it makes its outer layers balloon outward to an enormous size, and it cools that expanded surface down from white-hot to a duller red, which is where the name comes from in the first place. According to calculations published by astronomers Klaus-Peter Schroeder and Robert Conon Smith back in 2008, the Sun will eventually swell to roughly 256 times its current radius, an expansion so extreme that the star's surface would reach out and swallow the orbits of both Mercury and Venus along the way, shedding a substantial chunk of its own mass in the process. Whether Earth actually gets swallowed whole by that expansion, or just ends up orbiting dangerously close to a much larger, much brighter Sun, has genuinely been debated by scientists since 1924, when British mathematician James Jeans first raised the question, and the debate has swung back and forth for a full century since then, with different calculations reaching different conclusions as the underlying physics got refined. As the Sun sheds mass, its gravity weakens slightly, which should let planetary orbits drift outward and away from danger, the same way a spinning ice skater slows down and drifts wider when they let their arms out. At the same time, though, tidal drag between Earth and the Sun's puffed-up outer atmosphere pulls Earth inward, cancelling out a lot of that potential escape, a genuine tug-of-war between 2 competing physical effects playing out over millions of years. It's a strange kind of race to picture, one force gently letting the leash out while another quietly reels it back in, both acting on the exact same planet at the exact same time, over millions upon millions of years, with the final outcome depending on which effect simply happens to win by a slightly larger margin. The most detailed recent modeling comes down on the grim side of that tug of war. Earth most likely does not escape, and gets engulfed close to the tip of the Sun's red giant phase, somewhere around 7.6 billion years from now, by which point the Sun's surface will reach about 20% beyond Earth's current orbital distance, and will be shining roughly 3,000 times brighter than it does today, an intensity of light that's genuinely difficult to picture from where we're standing right now. Some scientists, including Don Korikansky at UC Santa Cruz, have floated genuinely wild hypothetical rescue plans, like nudging Earth's orbit outward over the course of 1 billion years using a repeatedly passing asteroid, engineering on a timescale most people never think to imagine, but that idea remains firmly in the realm of thought experiment rather than serious prediction. After that red giant phase burns through a relatively short window of helium fusion, lasting somewhere around 130 million years, itself a brief flicker compared to everything that came before it, the Sun sheds its outer layers entirely, briefly glowing as what's called a planetary nebula, a glowing shell of gas expanding outward into space, before settling down into what it will spend the rest of its existence as a white dwarf, a dense, roughly Earth-sized ember holding onto somewhere between about half and 2/3 of the Sun's original mass, slowly cooling for the ages that follow, essentially forever, at least on any timescale a human mind naturally works with. This exact fate, main sequence star, red giant, brief nebula, quiet white dwarf ending, is what's waiting for the vast majority of stars, similar in size to our own Sun, scattered across the universe. It's not some rare or unusual ending. It's closer to the default one, the standard exit for an entire class of stars just like ours, playing out billions of times over, across billions of galaxies, largely unwitnessed. There's something worth pausing on in that sequence of events, because compressed into a few sentences, it can sound almost tidy, almost gentle, and the actual physical scale involved is anything but. A star that has burned steadily for roughly 10 billion years, providing the light and warmth for whatever happened to be orbiting it that whole time, spends its final act destroying its own solar system in the process of dying, swelling outward past planets it once kept in careful, stable orbits, and swallowing at least some of them outright. And then, after all of that, after billions of years of steady burning and a comparatively brief, violent final act measured in mere hundreds of millions of years, what's actually left behind is startlingly small, an object roughly the size of Earth, holding most of the star's original mass packed down into a fraction of its former volume, destined to just sit there, cooling, for a length of time that makes the star's entire active lifetime look brief by comparison. The transition from star to white dwarf happens fast, relatively speaking. What follows it happens slow enough that slow barely describes it. That white dwarf ending isn't quite the simple, static conclusion it was once assumed to be either, and the correction to that picture came from real, recent, directly observed evidence rather than pure theory. Physicist Hugh Van Horn predicted back in 1968 that as white dwarfs slowly cool over billions of years, the carbon and oxygen packed into their interior should eventually undergo a genuine phase transition and crystallize into a solid, essentially the same basic process as liquid water freezing into ice, just happening at an interior temperature of roughly 10 million degrees Celsius instead of 0. For 50 years, that prediction sat there, mathematically sound but essentially unconfirmed, because no instrument had ever measured enough white dwarfs precisely enough to actually catch it happening. That changed in January of 2019, when a team led by Dr. Pierre-Emmanuel Tremblay at the University of Warwick, working with data from the European Space Agency's Gaia spacecraft, examined more than 15,000 white dwarf candidates within about 300 light-years of Earth, and found exactly what Van Horn had predicted 5 decades earlier. The evidence showed up as an unexpected pileup of white dwarfs sharing a particular color and brightness that didn't fit into any single tidy cooling track, a pattern astronomers now call the Q branch, and once the team worked through it, they realized these were stars caught in the act of crystallizing, releasing extra heat as they solidified in exactly the way a freezing process should. That extra heat measurably slows a white dwarf's cooling rate, which means some crystallizing white dwarfs can appear noticeably younger than they actually are, off by 1 billion years or more if the effect isn't properly accounted for. a real complication for how astronomers estimate the ages of old stars across the galaxy. It's a strange kind of disguise for a star to be wearing, its own slow freezing making it look younger than it really is, the astronomical equivalent of a face that doesn't show its true age because of what's quietly happening underneath the surface. Tremblay's team also proposed a refinement worth mentioning. They suspected the oxygen inside a cooling white dwarf crystallizes first and sinks toward the center, the same way sediment settles to the bottom of a riverbed, pushing the lighter carbon upward and releasing additional gravitational energy in the process, which helps explain why the observed cooling delay turned out to be even larger than the simplest models predicted. And this isn't some distant, abstract curiosity. It's directly relevant to our own sun's future, because the white dwarf our sun eventually becomes, billions of years from now, is expected to be made of exactly this same carbon-oxygen mixture, meaning this slow, quiet crystallization is a genuine, physically confirmed part of what's still ahead for the remnant of our own star, discovered not through theory alone, but through a spacecraft actually looking hard enough to see it happening. It's a strange thing to sit with, that a piece of the sun's own distant future has already been photographed, in effect, just wearing a different star's face. Somewhere out there, right now, among those 15,000 white dwarf candidates Gaia examined, there are almost certainly stars sitting at exactly the stage the sun's own remnant will eventually reach, quietly turning solid from the inside out, and nobody had any confirmed way of knowing that was even happening, until a spacecraft launched specifically to make an extraordinarily precise map of the galaxy's stars happened to be precise enough to catch it. Not every star gets that same quiet ending though, and it's worth pointing at a real, currently visible example of the more violent alternative, because you don't have to imagine it happening somewhere far off in the future. You can go outside on a clear winter night right now and look at it. Betelgeuse, the bright reddish star marking the shoulder of the constellation Orion, sits somewhere between about 500 and 650 light-years from Earth, depending on which measurement you trust, and it is, by nearly every account, nearing the end of its life. Unlike the Sun, Betelgeuse is a genuine giant, somewhere between 10 and 20 times the Sun's mass, with a radius so enormous that if you dropped it into the center of our own solar system, its surface would reach out past the orbit of Jupiter. Stars that massive don't get to end their lives quietly as a white dwarf. Instead, once they exhaust their nuclear fuel, their core collapses in a matter of seconds and triggers a supernova, one of the most violent and energetic events physics currently understands. For years, astronomers have simply said Betelgeuse will likely explode sometime within the next 100,000 years, soon, only in a cosmic sense. A 2023 study analyzing the star's pulsation patterns suggested it might be in the very late stages of core carbon burning and could be a great deal closer than that, possibly within just tens of years, a claim that understandably made headlines. More recent observations, though, using the Hubble Space Telescope and published in 2025, complicate that dramatic timeline. A team led by astronomer Andrea Dupree discovered that Betelgeuse actually has a previously unknown companion star, informally nicknamed Siwaha, orbiting roughly once every 2100 days, and that this companion's passage through Betelgeuse's outer atmosphere is what's actually been driving the star's famous, puzzling long-term brightness changes, the same changes once read as a possible warning sign of imminent explosion. That discovery has pushed most current thinking back toward the more conservative, within roughly 100,000 years estimate. Whenever it does finally happen, Earth is in no danger at all, sitting far beyond the roughly 150 light-year radius that would actually pose any threat. But whoever happens to be alive to see it will witness Betelgeuse briefly shine as bright as the half-moon, visible in broad daylight for months, a supernova unfolding in real time in the night sky humans have been looking up at for all of recorded history. There's something worth sitting with in the fact that Betelgeuse's light, whatever state the star is actually in right now, left it somewhere between 500 and 650 years ago. Every time someone looks up at Orion's shoulder tonight, they're seeing the star as it existed sometime around the late medieval or early modern period on Earth, not as it exists at this exact moment. If it has already exploded, if the star that shaped that reddish point of light no longer exists in any form, that information simply hasn't had time to reach us yet. A small, personal, present-day echo of exactly the same finite speed of light logic that eventually resolves Olbers's paradox on a much larger scale. Before zooming out to the scale of the whole universe, there's one more piece of context worth having, because it changes how you look at the night sky for the rest of this video, and it happens to be a puzzle that's been bothering astronomers for over 400 years, long before anyone understood the physics well enough to answer it properly. It's called Olbers' paradox, and the question at its center sounds almost embarrassingly simple. If the universe is packed with stars stretching out in every direction, the night sky should be blazing with light from horizon to horizon rather than mostly dark. Push the logic far enough, and if the universe really were infinite, eternal, and evenly filled with stars, then every single line of sight traced outward from Earth should eventually terminate at the surface of some star, somewhere, no matter which direction it pointed, no matter how far that line had to travel to get there. The sky should glow uniformly, all the time, everywhere, with no dark patches anywhere between the stars. It plainly doesn't, and that gap between a reasonable-sounding expectation and simple observation is the whole paradox in a nutshell. It's worth noticing, before getting into the history, just how much this simple question can carry once you actually follow it all the way through. A dark night sky sounds like the most unremarkable fact imaginable, something nobody would think twice about. And yet taking it seriously, actually asking why it's true rather than just accepting it, turns out to require knowing that the universe had a beginning, that stars have finite lifespans, and that space itself is expanding. Three of the biggest ideas in all of modern cosmology, all hiding behind a fact so ordinary that most people never once think to question it. This question is a good deal older than the name attached to it suggests, and its history is genuinely worth walking through, because it maps almost perfectly onto humanity's slowly improving understanding of what kind of universe we actually live in. According to historian Edward Robert Harrison, the earliest known version of it traces back to the 16th century, and an English astronomer named Thomas Digges, who was also the first person to lay out the Copernican, sun-centered model of the solar system in English, and who pictured an infinite universe scattered with infinite stars, a genuinely radical idea for its time. Johannes Kepler picked the problem up explicitly in 1610, arguing that the universe had to be finite and bounded, because an infinite one filled with stars would leave no dark gaps anywhere in the sky at all, a conclusion he found more believable than the alternative. Edmund Halley, yes, the comet astronomer, and a Swiss astronomer named Jean-Philippe Loyas de Chezeaux, both wrestled with versions of the same puzzle during the 1700s, working independently of each other, and de Chezeaux specifically proposed in 1744 that maybe interstellar dust was quietly soaking up all that distant starlight before it ever reached us, a solution that sounded reasonable enough at the time to be taken seriously for decades. It wasn't until 1823 that a German physician and amateur astronomer named Heinrich Wilhelm Olbers restated the problem in a published paper, and even though he was very much not the first person to raise it, having been beaten to it by Digges, Kepler, Halley, and de Chezeaux across more than 2 centuries of prior thinking, his name is the one that stuck to it permanently. Oddly enough, according to physicist Jim Al-Khalili, the paradox wasn't even formally attributed to and named after Olbers until sometime in the 1950s, nearly a century and a half after his paper was actually published, which says something about how slowly scientific credit sometimes gets sorted out. Olbers leaned on that same interstellar dust explanation de Chezeaux had proposed decades earlier, and it turned out to have a fatal flaw baked into it, one that took years for anyone to properly identify. Astronomer John Herschel eventually pointed out that if dust really were absorbing all that starlight, the dust itself would heat up over time until it reached thermal equilibrium with the stars around it, at which point it would start glowing just as brightly as the light it was supposedly blocking. Dust can delay light on its way to us, slow it down, redirect it. It can't make energy disappear entirely, and that's exactly what the dust explanation would have required. The actual answer, the one modern cosmology settled on, didn't fully arrive until 1858, when German astronomer Johann Heinrich von Mädler published the insight that a universe with a finite age solves the problem outright, an idea later popularized in an 1860 book by Friedrich Kaiser for a wider audience beyond professional astronomers. If the universe has only existed for around 13.8 billion years, light from stars sitting beyond that distance simply hasn't had time to reach Earth yet, no matter how bright those stars are or how long they've been burning. A limit built directly into the finite speed of light itself. Stack that on top of the fact that stars don't burn forever, meaning plenty of potential light sources have already gone dark long before their light could ever reach us. And the fact that the universe's own expansion stretches, or redshifts, light from extremely distant, rapidly receding galaxies clear out of the visible spectrum and into wavelengths our eyes simply can't detect. And the dark night sky stops being a paradox and starts being exactly what you'd expect from a universe that had a beginning, has an ongoing story, and is actively expanding the entire time light is trying to cross it. That redshifted invisible light isn't gone, by the way. It's exactly the same cosmic microwave background radiation Penzias and Wilson stumbled onto with their pigeon-infested antenna, the universe's earliest light, stretched by billions of years of expansion into wavelengths the human eye was simply never built to detect. NASA's own astronomers, discussing that 2016 discovery of far more galaxies than previously counted, pointed out that the declining number of visible galaxies over cosmic time, as galaxies merge together, and as light from the very earliest, faintest ones never manages to reach us at all, is itself part of the modern solution to this centuries-old riddle, tying a cutting-edge Hubble discovery directly back to a question first asked 400 years earlier. That last detail, a universe with a beginning and an ongoing story rather than a static, eternal backdrop, is the key that unlocks everything covered for the rest of this video, so keep it in mind as we go forward. Now the scale can properly zoom out using the exact framework astrophysicists Fred Adams of the University of Michigan and Gregory Laughlin, a postdoctoral researcher at UC Berkeley, when the two of them wrote their landmark book on this subject, built specifically to describe the far future of everything. They needed a scale that could stretch from the age we're living in right now all the way out to numbers with dozens and eventually hundreds of zeros attached. Numbers so large that writing them out in ordinary years would be genuinely unreadable. So instead of using years directly, they built what's called cosmological decades, where climbing one single step up the ladder means the universe has grown roughly 10 times older than it was at the previous step. We're sitting somewhere around the 10th cosmological decade right now, this very moment, watching this video. The story of the universe's death runs out to the 100th decade and well beyond that, and every single step past where we are today multiplies everything that came before it by another factor of 10, compounding in a way that quickly outpaces anything resembling everyday human intuition. Think of it this way. Moving from the 10th cosmological decade to the 11th isn't like adding one more year onto 13.8 billion. It's like living through the entire history of the universe again, 9 more times over, just to reach the next single step on the ladder. And there are 90 more steps after that one, each one dwarfing everything that came before it combined. They call the era we're currently living through the stelliferous era, a name that simply means filled with stars, and every galaxy, every constellation, every point of starlight anyone has ever looked up and seen belongs to this one single chapter of a much longer book. This chapter doesn't end all at once though, and it definitely doesn't end the same way for every star inside it. The biggest, brightest stars, stars like Betelgeuse, sitting up near the hot, luminous corner of the Hertzsprung-Russell diagram, are, ironically, the ones with the least staying power of all. They burn through their nuclear fuel so aggressively, so wastefully, that some of them live and die in as little as a few million years, which on a cosmic clock barely registers as a blink, over before it's really begun in any meaningful sense. They're the fireworks of the universe, spectacular, violent, and gone almost as soon as they arrive, burning bright, precisely because they refuse to pace themselves. The stars that actually outlast everything else aren't the big, dazzling ones at all. They're small, dim, and honestly, kind of forgettable if you happen to be looking straight at one. Red dwarfs, defined by astronomers as any star with less than half the mass of our Sun. Individually, a red dwarf isn't much to look at, easy to miss even from relatively nearby, let alone across interstellar distances, but they make up the overwhelming majority of stars in our galaxy, commonly cited at more than 75% of the roughly 200 billion stars in the Milky Way alone. What makes them the real long-term survivors is how stingy they are with their fuel. Adams and Laughlin describe them almost like misers, hoarding hydrogen and burning through it so slowly and carefully that a single red dwarf is expected to still be shining 10 trillion years from now, long after every sun-like star and every giant blue star in the universe, Betelgeuse included, has already gone through its own version of what our sun is going to go through. There's a kind of lesson embedded in that contrast, even if nothing in physics actually intends one. The stars that burn brightest, that dominate the night sky, that get named and mapped and pointed at by every stargazer who's ever looked up, are the ones with the least time left. The stars that outlast the entire rest of the universe combined are the ones so faint most people have never consciously noticed one. One of these red dwarfs isn't just a theoretical example either. It has a name, a known age, and a real planetary system already discovered around it. TRAPPIST-1 sits about 40 light-years from Earth in the constellation Aquarius, and it's home to 7 confirmed rocky, roughly Earth-sized planets, 3 or 4 of which orbit within its habitable zone, first announced in full by a Belgian-led research team in February of 2017. The star itself is tiny by stellar standards, only about 8 or 9% of the Sun's mass, and barely larger than the planet Jupiter, with a cool, dim surface glowing at around 2,566 Kelvin, well under half the Sun's surface temperature. It's already old, estimated at somewhere between 5.4 and 9.8 billion years, meaning it was likely already billions of years old before our own solar system even finished forming. And yet, by the standards of a red dwarf, TRAPPIST-1 is barely getting started. NASA exoplanet scientist Eric Mamajek described it about as vividly as anyone has. TRAPPIST-1, he said, is like a slow-burning candle that will shine for about 900 times longer than the current age of the universe. Other estimates put its total lifespan at somewhere around 10 trillion years, the same broad figure cited for red dwarfs generally, now attached to one specific, real, currently observed star with 7 real planets orbiting it. Those planets face real problems of their own, mind you. Because the habitable zone sits so close to such a dim star, all 7 worlds are almost certainly tidally locked, one side permanently facing TRAPPIST-1 and the other permanently facing away, and billions of years of stellar radiation have likely boiled away the equivalent of an entire ocean's worth of water from most of them, leaving only the 2 outermost planets with a real chance of holding on to substantial water or atmosphere today. There's something almost vertiginous about that comparison if you actually sit with it for a second, slowing down long enough to let the 2 numbers sit side by side in your head rather than sliding past each other. TRAPPIST-1's 7 planets, whatever their odds of actually holding on to life across that kind of span, have a stage to work with that our own solar system simply doesn't. Earth has, at the outside, something like 1 billion years left before the oceans start boiling away, and a little under 5 billion more after that, before the Sun swallows the inner solar system outright. TRAPPIST-1's planets, assuming they can survive their star's early violence and hold on to some kind of atmosphere, are looking at a stage roughly 10,000 times longer than that, a runway so long that billions of years stops being the right unit to even measure it in. That longevity has led some astronomers to a genuinely strange conclusion about our own place in cosmic history. In 2016, astrophysicist Avi Loeb of the Harvard-Smithsonian Center for Astrophysics led a study modeling the probability of life emerging across the full span of cosmic time, and the results suggested that the odds of life existing anywhere in the universe are roughly 1,000 times greater in the distant future than they are right now, simply because red dwarfs offer so much more total time for life to get started and take hold. Loeb put it directly: if you ask when life is most likely to emerge, the naive answer is now, but the actual chance of life grows much higher the further into the future you look. By that logic, life on Earth today might genuinely be, in his own word, premature, an early guest arriving well before the party has really started. There's a particular kind of humility built into that framing worth sitting with. It doesn't say humanity is unlikely, or accidental, or a cosmic fluke in the usual sense. It says humanity showed up on time by its own local clock, the 4.5 billion year clock of one ordinary solar system, but arrived absurdly early by the clock of the universe as a whole, like a guest who checked the date correctly, but somehow missed that the party runs for 10 trillion years. It's not a settled conclusion, and red dwarfs come with real complications of their own, since young red dwarfs go through a violently active phase, roughly their first billion years or so, flaring intensely enough to potentially strip the atmosphere off any nearby planet, and even old, supposedly quiet red dwarfs can still surprise you. Barnard's star, one of the closest stars to our own Sun at just 6 light-years away, and estimated to be 7 to 12 billion years old, more than twice the Sun's current age, was long assumed to be a calm, inactive star, right up until astronomers caught it, producing a significant, unexpected flare in 1998. It's a useful reminder, tucked into an otherwise reassuring statistic about red dwarfs settling down as they age, that mostly calm and permanently calm aren't the same thing, and that a star billions of years past its violent youth can still, on an unpredictable afternoon, do something nobody watching it expected. Loeb's premature life idea also happens to offer one quiet, non-catastrophic answer to a much older, much more famous puzzle, worth a brief detour here, because the two questions turn out to be more connected than they first appear. Back in the summer of 1950, physicist Enrico Fermi, a Nobel laureate who had built the world's first controlled nuclear reactor and later worked on the Manhattan Project, was walking to lunch at Los Alamos National Laboratory with a few colleagues, the conversation drifting through flying saucers and the odds of faster-than-light travel, when he apparently blurted out, almost out of nowhere, "But where is everybody?" Nobody at the table needed it explained. Given how many stars exist, how many of them are billions of years older than our own Sun, and how much time an advanced civilization would have had to spread across a galaxy, even at slow sublight speeds, Fermi's simple question pointed at a real and uncomfortable gap. If intelligent life is even moderately common, the galaxy should already be full of evidence for it, and it plainly isn't. That gap became known as the Fermi paradox. And just like Olbers and his dark night sky, Fermi wasn't actually the first person to raise the underlying idea. Versions of it show up in writing going back to the 1600s, but his name is the one history attached to it. Dozens of proposed explanations have piled up since, ranging from the idea that interstellar travel is simply too hard, to the unsettling Great Filter hypothesis proposed by economist Robin Hanson in the 1990s, which suggests some brutally difficult step stands between lifeless chemistry and a galaxy-spanning civilization, one that almost nothing successfully gets past, with genuine, ongoing scientific disagreement about whether humanity has already cleared that filter or still has it waiting somewhere ahead. There's a genuinely uncomfortable asymmetry built into that idea, one worth spelling out plainly rather than glossing over. If the filter sits somewhere in humanity's past, in the sheer improbability of life beginning at all, or of simple cells becoming complex ones, or of complex life ever developing real intelligence, then the silence out there is actually good news, evidence that the hardest part is already behind us. But if the filter still lies ahead, if it's something like a civilization's own technology eventually turning against it, then that same silence stops being reassuring and starts looking like a warning, a graveyard of civilizations that all made it exactly as far as we have, and then, for one reason or another, didn't make it any further. Nobody currently knows which version is true, and that uncertainty is precisely what makes the question still worth asking. A 2018 Oxford University analysis, rerunning the classic Drake equation with updated statistical methods, even concluded there's a substantial chance, somewhere between roughly 38 and 85% by their estimate, that humanity is entirely alone within the observable universe. Part of what makes the silence so striking is that scientists actually have a rough framework for what an advanced civilization's presence should look like from a distance, and it isn't subtle. In 1964, Soviet astrophysicist Nikolai Kardashev proposed ranking hypothetical civilizations not by their culture or their technology exactly, but simply by how much energy they're able to harness and use. Presented at a conference in the Armenian SSR, specifically as a practical guide for astronomers listening for alien radio signals. A Type 1 civilization, in his scheme, commands roughly 10 to the 16th power watts, the full energy budget of an entire planet. A Type 2 commands roughly 10 to the 26th power watts, the entire output of its home star, something like a Dyson sphere might theoretically capture. A Type 3 commands roughly 10 to the 36th power watts, the combined output of every star in an entire galaxy. A civilization whose energy use would be genuinely detectable across intergalactic distances if it existed. Humanity, for context, doesn't even reach Type 1 yet. Global energy consumption today sits around 18 terawatts, roughly 1,000 times below that first threshold, putting us, by Carl Sagan's later decimal refinement of the scale, at something like Type 0.7. Kardashev's own team even tried putting the framework to a real test almost immediately, studying a radio source called CTA-102 from a Soviet deep space station between 1963 and 1965, specifically looking for a possible Type 3 signal, and in April of 1965 briefly announced to the press that they might have found one, before further observation showed the source was just a natural quasar, not an alien civilization after all, an early, very real false alarm baked right into the history of this whole line of thinking. No confirmed Type 2 or Type 3 signal has ever been detected in the 6 decades since, which only sharpens Fermi's original question rather than answering it. Loeb's 2016 red dwarf study offers a gentler alternative to all of that grim silence. Maybe intelligent life isn't rare, self-destructive, or blocked by some impassable filter at all. Maybe it's simply early, showing up in a universe that's barely gotten started, long before the trillion-year stretch when red dwarfs like TRAPPIST-1 will still be quietly burning and conditions for life, statistically, are expected to be at their best, long before any civilization anywhere has had the time it might actually need to climb Kardashev's ladder at all. That number alone, 10 trillion years, deserves a genuine second of reflection, because the universe itself is not yet 14 billion years old. The longest-lived stars still have a life ahead of them, roughly 700 times longer than the entire history of the universe up to this point, meaning, if you could somehow compress the universe's entire existence so far down into a single day, those red dwarfs would still have hundreds of days left to go after that day was over. And even these stubborn little stars don't burn forever. Eventually, across the whole universe, galaxies run out of the raw hydrogen gas needed to build brand new stars in the first place. And once that happens, star formation simply stops everywhere, permanently, with nothing left to restart it. No more stellar nurseries, no more newborn suns lighting up nebulas, just the long, slow fade of whatever's already burning, dimming, star by star, across every galaxy simultaneously. Adams and Laughlin's calculations put the moment the very last, lowest mass red dwarfs finally flicker out at around 100 trillion years after the Big Bang, and that marks the true close of the stelliferous era. When it happens for the last time. No more stars, ever, anywhere, in any galaxy, in the whole of the observable universe. Before leaving the stelliferous era behind for good, it's worth pausing on something much closer to home that fits neatly inside this same chapter, unfolding on a much shorter, far more personal timescale than the 100 trillion year fade of the last red dwarfs, the fate of our own galaxy. Andromeda, the nearest large galaxy to the Milky Way, sits about 2.5 million light-years away right now, and it's closing that gap at roughly 110 kilometers per second, a speed measured through the blue shift of its light, the same basic principle used to measure the pitch of an ambulance siren as it approaches. The long-standing prediction, built on 2012 Hubble Space Telescope measurements, was that the two galaxies would collide in something like 4 to 4.5 billion years, then fully merge into one giant elliptical galaxy over the following several billion years, forming what astrophysicist Avi Loeb and his then postdoc T.J. Cox nicknamed Milkomeda in a 2007 paper, a name that stuck in both scientific and popular writing ever since. A more recent 2022 simulation pushed that timeline out a bit further, suggesting a close pass around 4.3 billion years from now, followed by a full merger roughly 6 billion years after that, a somewhat longer runway than the earlier estimate. Here's the twist worth knowing, and it's a genuinely current one, not something settled decades ago and left untouched since. As recently as 2025, astronomer Till Sawala and his colleagues reanalyzed the collision using newer data from the Gaia spacecraft and Hubble, data that simply wasn't available back in 2012, and found that the odds of an outright Milky Way Andromeda collision are actually lower than previously believed. This isn't quite the settled certainty it's often presented as in older documentaries and older explainer videos. It's an open, active area of research, being revised in real time as better instruments and more precise measurements come online, which is genuinely part of what makes this field exciting to follow, rather than a fixed, finished story. It's worth pausing on what actually changed between 2012 and 2025 to cause that particular shift in the odds, because it's not that Andromeda suddenly slowed down, sped up, or changed its overall course. It's that measuring a galaxy's sideways motion across the sky, its tangential velocity, rather than just its straight-line approach speed, is an extraordinarily difficult thing to do precisely, and the newer Gaia data simply gave astronomers a sharper handle on a number that had always carried more uncertainty than the confident 4.5 billion years figure usually let on. If the merger does happen, individual stars essentially never collide with each other directly, because the space between stars inside a galaxy is so vast that a direct collision is statistically almost negligible, and simulations suggest our solar system would most likely just get flung into a new, wider orbit within the resulting elliptical galaxy, rather than being destroyed outright. The supermassive black holes at each galaxy's center, though, are expected to eventually spiral together and merge fully, and in the final moments before that merger, they'd radiate gravitational waves carrying the power of roughly 10 quintillion suns, a genuinely staggering release of energy tucked inside an otherwise slow, quiet process spanning billions of years of gradual approach. It's worth letting that number actually land for a second. 10 quintillion suns worth of power, released not as light but as a ripple in space-time itself, meaning nothing would visibly flash or brighten anywhere in the sky. The entire event would be, in an ordinary optical sense, almost silent, an unimaginable amount of energy pouring out of two colliding black holes with nothing to see, only something to feel, if you happen to have an instrument sensitive enough to measure space-time itself flexing. That prediction isn't purely theoretical speculation either, which is worth pausing on, because for most of the 20th century, it actually was. Gravitational waves, ripples in the fabric of space-time itself, were part of Einstein's general theory of relativity from as far back as 1916, but for nearly 100 years afterward, nobody had ever directly detected one. That changed on September 14, 2015, when the two detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, simultaneously picked up a signal matching almost exactly what theory predicted two black holes spiraling into each other and merging should look like. The event, later named GW150914, involved two black holes of about 36 and 29 solar masses, merging into a single black hole of about 62 solar masses, located roughly 1.3 billion light-years away, with the difference, about 3 suns' worth of mass, radiated away entirely as gravitational waves in a fraction of a second, one of the single most energetic events humans have ever directly measured. The discovery wasn't announced publicly until February of 2016, and LIGO's Kip Thorne described the moment in a way that stuck with a lot of people since. For decades, he said, physicists had only ever seen space-time when it was calm, like a glassy, undisturbed ocean, and this was the first time anyone had witnessed the ocean in a storm, with actual crashing waves. In the years since that first detection, LIGO and its partner observatory Virgo have confirmed roughly 50 more mergers of black holes and neutron stars, turning what was once purely theoretical into an entirely new, working branch of astronomy. It's worth appreciating just how strange a detector like LIGO actually is, mechanically. To catch a signal like GW150914, the instrument had to measure a distortion in the distance between its mirrors, far smaller than the width of a single proton, an effect so faint that for most of the 20th century, gravitational waves were widely treated as a real, but permanently undetectable prediction, something general relativity clearly required, but that no realistic technology would ever be sensitive enough to actually measure. It took nearly a century of steadily improving engineering, culminating in LIGO's design, to prove that assumption wrong. And this matters directly for the Andromeda story, because that 10 quintillion suns figure predicted for the eventual Milky Way-Andromeda black hole merger isn't a guess dressed up in impressive-sounding numbers. It's calculated using the exact same equations LIGO confirmed actually describe reality back in 2015, meaning a merger that won't happen for roughly 10 billion years is being predicted using physics that has already been tested and verified, right here, right now, in the present. Once every star in the universe, from the largest to the smallest, has finally gone out, the universe doesn't just become empty, it shifts into what Adams and Laughlin call the degenerate era, a name borrowed from the physics term for the extreme, crushed states of matter left behind inside dead stars, states so dense that ordinary rules of matter start bending under the pressure. This era stretches from roughly 10 to the 15th power years out to 10 to the 39th power years, an almost incomprehensible span, dwarfing even the 100 trillion year stelliferous era that came before it. And it belongs entirely to stellar corpses, white dwarfs, brown dwarfs, neutron stars, and black holes. Of those remnants, neutron stars are worth a moment of their own, because their discovery is one of the more remarkable detective stories in 20th century astronomy. A neutron star forms when a massive star, one considerably heavier than our Sun, explodes as a supernova, and its core collapses under its own gravity into something almost unimaginably dense, somewhere between 1.5 and 3 times the mass of our Sun, crushed down into a sphere only about 20 kilometers across, barely wider than a city. A single teaspoon of that material would weigh roughly 1 billion tons if you somehow brought it back to Earth. Nobody had ever observed one directly until 1967, when a Cambridge University graduate student named Jocelyn Bell Burnell, working under her advisor Anthony Hewish, noticed something strange buried in reams of paper printouts from a radio telescope she had personally helped build. A signal pulsing with almost perfect mechanical regularity, once every 1.33728 seconds, over and over, without fail. It was so precise that she and her team briefly, half seriously, nicknamed the source LGM-1 for Little Green Men, wondering if they'd stumbled onto a signal from an alien civilization. Once they found several more similarly precise pulsing sources scattered across completely different parts of the sky, the alien explanation fell apart, and theorists quickly converged on the real answer. These were rapidly spinning neutron stars, sweeping narrow beams of radiation around like a lighthouse, visible from Earth only in the brief instant that beams swept directly across our line of sight. The discovery was published in the journal Nature in February of 1968, and the press dubbed these objects pulsars. In 1974, the Nobel Prize in Physics was awarded for the discovery, but it went to Hewish and fellow astronomer Martin Ryle, not to Bell Burnell herself, despite her being the one who actually found the signal and pursued it, a decision that drew open protest from other scientists at the time. Bell Burnell later said she felt the prize had gone to the appropriate people given her status as a student at the time, but the story didn't end there. In 2018, she was awarded the $3 million Breakthrough Prize in Fundamental Physics, and she donated the entire amount to fund PhD scholarships for women, underrepresented minorities, and refugee students entering physics, turning a decades-older mission into something that's still funding new scientists today. It's a genuinely satisfying kind of full circle, worth pausing on. A discovery originally made by a student who wasn't given the recognition it deserved, eventually became, decades later, the very thing funding a new generation of students who might otherwise have faced the same kind of overlooked start she once did. Astronomers now estimate there are tens of millions of pulsars scattered across our galaxy alone, and every single one of them is, in effect, a preview of what the degenerate era looks like. Matter crushed down to its absolute physical limit, still spinning, still faintly signaling, long after the star it used to be has stopped existing in any recognizable form. There's something fitting about the fact that these objects were found by accident, buried in a young researcher's data, rather than by anyone deliberately setting out to look for crushed stellar corpses. So much of this video's account of the far future rests on exactly that kind of pattern, careful people looking closely at ordinary-seeming data and noticing that something in it doesn't quite fit, whether that's a strange radio pulse repeating every 1.3 seconds, an unexplained hum in an antenna, or a pile-up of white dwarfs that shouldn't share the same color and brightness by chance. No new light comes from nuclear fusion anywhere in the universe anymore once this era gets going, because there's simply nothing left to fuse, no fresh hydrogen anywhere to feed a new star into existence. That doesn't mean nothing is happening, though. During the earlier stretch of the degenerate era, white dwarfs, the compressed, roughly Earth-sized remnants left behind by dying sun-like stars, begin absorbing something invisible that's been drifting through the universe the entire time, unnoticed and untouched: dark matter. It's worth pausing here to be honest about exactly how mysterious dark matter still is, even today, in the present. Its existence was first inferred all the way back in 1933 by Swiss astronomer Fritz Zwicky, who noticed that visible matter in galaxy clusters couldn't account for the gravitational forces he was observing holding those clusters together, and it was further confirmed in the 1970s when astronomer Vera Rubin and her colleague W. Kent Ford studied how fast stars orbit within spiral galaxies, and found that stars far from a galaxy's center were moving just as fast as stars near the middle, which shouldn't happen unless there was a huge amount of unseen mass out there we simply can't detect directly. It's worth noting just how long a gap sits between those two moments: Zwicky's original 1933 observation and Rubin's confirming work decades later. For most of that stretch, Zwicky's findings sat on the edges of mainstream astronomy, treated by many as an interesting anomaly rather than evidence of an entirely new category of matter making up most of the universe. It took Rubin's far more detailed, far more systematic measurements of galaxy rotation, decades after Zwicky first raised the alarm, to convince the field that something genuinely strange was going on, and even then, the actual identity of whatever's causing it remains just as unknown today as it was when Zwicky first noticed the discrepancy nearly a century ago. In all the decades since, despite dedicated searches using detectors with names like Xenon 1T, Panda X2, DarkSide, and Super CDMS, hunting for theoretical dark matter particles called WIMPs, and other experiments like ADMEX hunting for a different candidate called axions, not a single dark matter particle has ever been directly detected in any laboratory on Earth. Precision cosmological measurements confirm that ordinary matter, the stuff making up stars, planets, and every living thing, adds up to less than 5% of the universe's total mass and energy, meaning the vast majority of what's out there, including the dark matter this exact part of the story depends on, remains genuinely, fundamentally unexplained. Whatever dark matter actually turns out to be, as these dark matter particles get trapped inside a white dwarf, they start annihilating each other, and that annihilation becomes the single dominant energy source left in the universe, taking over the job nuclear fusion used to handle inside living stars for billions of years beforehand. It's a strange kind of afterlife for a dead star, powered not by fuel it once had and used up, but by ghostly particles it happens to be sweeping up as it drifts silently through space, an energy source built entirely on accident rather than design. There's an odd symmetry worth noticing here too. Right now, in the present, dark matter is best known for what it does at galaxy scale, holding spiral galaxies together, bending the orbits of outer stars in ways ordinary matter alone can't explain. Billions of years from now, in the degenerate era, that same unexplained substance switches roles entirely, going from a passive gravitational glue holding galaxies together to an active fuel source keeping the last embers of dead stars faintly warm. Same mystery substance, completely different job, at two wildly different points in the same 14 billion year story so far. That energy source runs out too, eventually, the same way every energy source in this story eventually runs out. By roughly the 30th cosmological decade, around 10 to the 30th power years, the available dark matter is depleted, and this particular chapter of borrowed light closes for good. It's worth mentioning that the degenerate era isn't a completely silent, motionless stretch either, even with every star already gone dark. Every so often, something genuinely dramatic still happens, a brief flare of activity in an otherwise still and quiet universe. Two brown dwarfs, failed stars too small to have ever ignited proper fusion on their own during the earlier, star-filled era, can collide with each other, and that collision can generate enough heat and pressure to briefly spark a real, if small, new star. One that can then go on burning steadily for trillions of years afterward. A genuine second wind, for two objects that never quite made it as stars the first time around. There's something almost hopeful about that particular detail, tucked away inside an era mostly defined by decay. Two objects that failed at the one thing stars are supposed to do, fusing hydrogen, get a second chance at it, entirely by accident, simply by happening to run into each other at the right speed and angle after unfathomable stretches of drifting through an otherwise darkened universe. It's the closest thing this whole story has to a rebirth, even if it's a rebirth built on collision rather than anything resembling intention. Occasionally, two white dwarfs collide, and when that happens, the result is a supernova, a real explosion, bright and violent, briefly rocking through an otherwise dark and silent galaxy like a single firework going off in an empty stadium. So even here, in an era defined mostly by decay and slow fading, the universe still manages the occasional flare of genuine drama scattered across unimaginable stretches of quiet. Proof that entropy doesn't mean total stillness, just an overall unstoppable trend toward the end. The final act of the degenerate era hinges on something physicists have never actually observed happening, and it's important to be upfront about that, because everything that follows depends on this theoretical process turning out to be real rather than simply a mathematically elegant idea. Certain grand unified theories, the branch of physics trying to stitch together forces that sit beyond what the standard model currently covers, predict that protons, the particles sitting at the core of every atom in existence, in every star, every planet, every living thing, are not actually permanent. According to these theories, protons should eventually decay, violating a conservation law the rest of physics currently treats as absolute and unbreakable. The version of this idea in Adams and Laughlin's book, published back in 1999, cited a predicted proton lifetime around 10 to the 30th power years, a span roughly a quintillion times longer than the entire current age of the universe. But it's worth updating that number with what real experiments have actually found in the years since the book was written. Because science, unlike the numbers in this story, doesn't sit still. The leading real-world search for proton decay happens at a facility called Super Kamiokande, a massive underground water detector in Japan that's been running since the 1990s, buried deep beneath a mountain, specifically to shield it from interfering cosmic rays. It has never once detected a confirmed proton decay event in any of the specific ways physicists have looked for one, across decades of continuous operation. But every year of silence lets scientists rule out shorter and shorter possible proton lifetimes, pushing the known lower limit further out with each passing year of null results. There's a peculiar kind of scientific patience built into an experiment like that, worth acknowledging directly. Most experiments are built to detect something. Super Kamiokande has spent decades essentially proving a negative, and every single year it fails to see a proton decay is still a meaningful, publishable, useful result, because it narrows down what's still possible rather than confirming what's real. It's the kind of research that only makes sense on timescales longer than any one scientist's career. Built by one generation of physicists, with the explicit understanding that a future generation, using better versions of the same detector, will be the ones who either finally see something or keep pushing the limit out further still. As of its most recent published results, Super Kamiokande has established that a proton's lifetime must be at least 2.4 times 10 to the 34th power years for one possible decay pathway, at least 1.6 times 10 to the 34th power years for another, and at least about 5.9 times 10 to the 33rd power years for a third. Every one of those numbers is already larger than the 10 to the 30th power figure the original 1999 book cited, which means the simplest early predictions for proton decay have already been ruled out by direct experiment, quietly, without much public fanfare. More complex versions of grand unified theory, predicting longer proton lifetimes, remain untested and still very much on the table, waiting for the next generation of even more sensitive detectors. And in a nice bit of scientific irony worth appreciating, the detectors built specifically to hunt for proton decay ended up making their real mark somewhere else entirely. Kamiokande and Super Kamiokande's detection of neutrinos, including neutrinos from a nearby supernova in 1987 and from the Sun itself, contributed directly to two separate Nobel Prizes in physics being awarded for neutrino research, a scientific plot twist nobody involved in building the original detector fully anticipated. If proton decay does happen the way these theories predict, whatever the true timescale turns out to be once experiments finally catch it in the act, it slowly and patiently dismantles whatever ordinary matter is still left anywhere in the cosmos, atom by atom, with no exceptions and no survivors. Once even the leftover white dwarfs and neutron stars are stripped down atom by atom through this process, something almost poetic happens, at least by the standards of theoretical physics. A white dwarf being consumed from within by proton decay is calculated to generate only about 400 watts of power, which Adams and Laughlin point out is roughly enough to run a few household light bulbs. Not power a city, not light up a solar system, just a handful of light bulbs from what used to be an entire star, an entire sun, reduced to something you could plug into a single household outlet. Zoom out further, and an entire galaxy's worth of these decaying remnants, all combined, would together produce less total light than a single ordinary star like our own sun puts out today, an entire galaxy dimmer than one star. It's worth sitting with that image for a moment. Every white dwarf, every neutron star, every leftover ember from every galaxy that ever existed, all of it combined, glowing more faintly than our own sun does on an ordinary afternoon. That's not a metaphor for decline. It's a literal, calculated figure, the actual measurable output of trillions of stellar remnants added together, and it's dimmer than one working star. As this process finishes grinding through the last scraps of matter, the degenerate era finally closes, somewhere around 10 to the 39th power years after the beginning of everything, according to the original framework, though the true closing date depends entirely on whatever the actual proton lifetime turns out to be once, or if it's ever directly measured. What's left after that isn't nothing. It's black holes, entering what Adams and Laughlin call the black hole era, stretching from roughly the 40th cosmological decade out past the 100th. Black holes stand out as the only significant structures still standing, because unlike everything else in the universe, they're completely untouched by proton decay, immune to the process that has, by this point, dismantled everything else. While every other form of matter has been quietly disintegrating around them across tens of cosmological decades, black holes have simply been sitting there, occasionally growing larger by pulling in whatever drifting material happens to fall within reach, more patient than anything else this story has covered so far, outlasting every star, every planet, every ordinary atom, including every last pulsar that once spun so precisely in the dark. Our own galaxy already has one of these patient giants sitting quietly at its center, worth mentioning here because it's not some distant, hypothetical example, but something astronomers have now genuinely photographed. Sagittarius A, the supermassive black hole anchoring the Milky Way, sits about 27,000 light-years from Earth and weighs in at roughly 4.3 million solar masses, a figure pinned down over decades by carefully tracking the orbits of individual stars swinging around it, work precise enough to earn astronomers Reinhard Genzel and Andrea Ghez a share of the 2020 Nobel Prize in Physics. On May 12, 2022, the Event Horizon Telescope collaboration released the first actual image of it, a bright, slightly lopsided ring of light wrapped around a dark central shadow, built from data that had actually been collected 5 years earlier, in April of 2017, using 8 radio observatories scattered across the planet, linked together into a single, Earth-sized virtual instrument. It took more than 300 researchers at roughly 80 institutions about 5 years to turn that raw data into a usable image. And oddly enough, our own galaxy's black hole turned out to be harder to photograph than a far more distant one the same team had already imaged in 2019, the black hole at the center of galaxy M87, simply because Sagittarius A is smaller and the gas swirling around it changes shape in minutes rather than days, like trying to photograph something that won't hold still. There's something almost counterintuitive worth flagging in that detail. Nearness usually makes things easier to study, not harder, and yet here, being closer worked against the astronomers, because a smaller black hole means faster changing surroundings, and faster changing surroundings mean the picture has to be assembled from data that's constantly shifting underneath it, the astronomical equivalent of trying to take a long exposure photograph of something that refuses to sit still for the shutter. The Event Horizon Telescope team called the achievement the dawn of a new era of black hole physics, and it's worth sitting with the fact that the object in that picture, sitting at the exact center of our own galaxy, is already living out the opening stretch of the same patient, multi-billion-year story every other black hole in this video is eventually going to go through. Every star described earlier in this video, every red dwarf that will still be shining 10 trillion years from now, every white dwarf slowly crystallizing, is, at this very moment, orbiting that same object 27,000 light-years away, tracing paths around it, the way Earth traces a path around the Sun, just on a galactic scale instead of a planetary one. It's strange to think that the same physics governing something photographed in 2022, sitting quietly at the center of the galaxy we happen to live in, is the physics that eventually determines how the whole black hole era plays out, tens of cosmological decades from now. And yet even black holes, objects so powerful that not even light can escape their gravity, are not permanent fixtures either. Nothing in this story is, in the end. In the mid-1970s, physicist Stephen Hawking demonstrated something that completely reshaped how scientists think about black holes. That quantum effects occurring right at the edge of a black hole's event horizon cause it to emit a faint, steady stream of radiation, now known as Hawking radiation, and that this radiation slowly bleeds away a black hole's mass over time, drop by drop, particle by particle. It sounds almost gentle compared to everything else in this story, a slow leak instead of a violent ending. But the timescales involved are so vast that slow barely begins to capture it. How long this actually takes depends entirely on how massive the black hole is to begin with, and the numbers stretch dramatically further apart the bigger you go, in a relationship that isn't simply linear but compounds the larger the black hole gets. A black hole roughly the mass of our own Sun is calculated to take approximately 10 to the 67th power years to fully evaporate away to nothing, a number so large it makes the entire age of the universe so far, all 13.8 billion years of it, look like a rounding error too small to even bother writing down. Physicist Don Page worked out the details of this back in 1976, calculating that the smallest known black holes would need around 10 to the 66th power years to fully evaporate, while a supermassive black hole weighing in at around 100 billion times the mass of our Sun would need more than 10 to the 100th power years, a number known as a googol, before it finally disappeared completely. A black hole the size of our own galaxy's Sagittarius A, at roughly 4 million solar masses, sits somewhere in between those extremes, on an evaporation timescale so far beyond anything covered so far in this video that no source appears to have bothered publishing an exact figure for it specifically, presumably because the difference between absurdly incomprehensibly long and slightly more absurdly incomprehensibly long stops being a meaningful distinction at this scale. That's worth sitting with as a general pattern across this entire video, actually. Past a certain point, the exact digit sitting in front of all those zeros stops mattering nearly as much as the sheer number of zeros themselves. Whether a given black hole finishes evaporating at 10 to the 67th years or 10 to the 70th years is, in every practical sense that matters to a human being watching this video, the same answer: longer than anything else in this story, longer than anyone will ever be around to check. It helps, maybe, to try building some kind of comparison for a number like 10 to the 67th, even though nothing in ordinary experience is remotely close to large enough to make the comparison feel intuitive. The universe so far has existed for a little under 10 to the 11th years. 10 to the 67th is not 10 times larger than that, or 1,000 times, or even 1,000,000,000,000 times. It's larger by a factor of 10, followed by 56 more zeros, a gap so vast that doubling the age of the universe, or squaring it again, still wouldn't close more than a rounding error's worth of the distance. Numbers like this are really a kind of admission. Physicists working with them would probably say, an honest way of writing down, we don't have a comparison for this, rather than a number anyone is meant to actually picture. And that's before even reaching the Google scale figures attached to the largest supermassive black holes, numbers so far removed from anything countable that the physics describing them is more reliable, in the end, than any attempt at human intuition ever could be. Yale researcher Priyamvada Natarajan put that scale of time about as plainly as it can be put. Compared to how long it takes a supermassive black hole to evaporate, the entire age of the universe so far isn't even a meaningful fraction of that time span, and as far as anyone studying it is concerned, it might as well be eternity. That's not an exaggeration for effect, either, not a scientist reaching for a dramatic soundbite. When the Event Horizon Telescope captured its now famous first image of a supermassive black hole in 2017, an image that made headlines around the entire world, physicists calculated that the black hole at the heart of galaxy M87 wouldn't finish evaporating for at least 10 to the 94th power years, meaning any Hawking radiation coming off it is, and will remain for the foreseeable future, and likely forever, far too faint for any instrument humanity could ever conceivably build to actually detect directly. There's a strange kind of asymmetry worth noting between that image and the process it's actually connected to. The picture itself, a bright ring of glowing gas wrapped around a dark shadow, was captured, processed, and shared with the public within a handful of years, a genuinely fast turnaround by the standards of major astrophysical discoveries. The process the picture is quietly, invisibly hinting at, the black hole's own eventual evaporation, won't finish for a length of time so vast that won't finish soon doesn't even begin to describe it. Humanity managed to photograph an object midway through a process that started before recorded history and won't conclude until long after every other fact in this video has already happened. A snapshot of one single, ordinary moment inside a story that has barely begun. Interestingly, this is a different kind of black hole evidence than the gravitational wave detections described earlier around the Andromeda merger. LIGO's discovery confirmed that black holes exist, collide, and merge exactly as general relativity predicts. Hawking's theoretical work, by contrast, describes something almost the opposite process, the extremely slow bleeding away of a black hole rather than a sudden merger, and that particular prediction remains entirely unconfirmed by direct observation, a theoretical idea still waiting for its own version of a GW1F914 moment, if such a moment is even possible, given how faint the signal would be. In a strange way, that makes Hawking radiation the most trusted, unconfirmed idea in all of modern physics. Almost every physicist working in the field treats it as essentially certain to be correct, built as it is on well-established quantum mechanics, applied to a well-established feature of general relativity. And yet, because the actual radiation predicted from any realistic astrophysical black hole is so unimaginably faint, humanity may never build an instrument capable of directly measuring it, not in 100 years, not in 1,000, possibly not ever. It's a rare case in science where near-universal theoretical confidence and a near-total lack of observational proof are expected to coexist permanently. What makes the very end of a black hole's life genuinely strange is that it doesn't fade out evenly the whole way through, unlike almost everything else described in this video, which tends to fade gradually and steadily. As a black hole loses mass, it actually gets smaller and hotter, and the hotter it gets, the faster it radiates away even more mass, which makes it hotter still, a runaway feedback loop that keeps accelerating on itself. It means that after unimaginable stretches of near-total silence, stretches longer than everything else covered in this video combined many times over, the final moments of a black hole's existence unfold in a rapid, energetic burst, releasing whatever mass remains almost all at once, in what some physicists have informally nicknamed a kind of white hole event. There's a strange shape to that ending worth noting, because it's almost the mirror image of how this whole story began. The universe opened with an unimaginably hot, dense, rapid event, the Big Bang, followed by trillions upon trillions of years of slow, patient cooling and fading. The very last physical structures left in that same universe, the final evaporating black holes, close out their existence with a comparatively sudden, hot, energetic burst of their own. A small, scattered echo of the same kind of event that started everything, played out one final time, one black hole at a time, across the emptiest, coldest, quietest stretch of time this story has covered. That's the closest thing left in this entire story to a dramatic, explosive ending, and it only arrives after a wait longer than almost anything else covered here so far. A genuinely fitting, almost poetic way for the last physical structures in the entire universe to finally go. Now, everything walked through so far, from red dwarfs fading out around 100 trillion years, all the way through black holes evaporating around 10 to the 100th power years, assumes one particular long-term fate for the universe as a whole. And it's worth being honest that this isn't the only scenario physicists take seriously, even if it's the one this entire video has been building toward. It's simply the one best supported by current evidence, and current evidence, by definition, can always be updated by better evidence later. Cosmologists generally lay out three broad possibilities, and which one actually happens comes down to the precise behavior of dark energy, the mysterious force that's been accelerating the universe's expansion since at least 1998, when two independent research teams discovered it by studying distant exploding stars called Type Ia supernovae, a discovery significant enough to later earn a Nobel Prize. Current best estimates put dark energy at roughly 68 to 70% of the universe's total mass and energy, dark matter at around 26 to 27%, and ordinary matter, meaning everything anyone can actually see directly, including every star, planet, and person who has ever lived, at only about 5% of the total, a genuinely humbling ratio to sit with. Every single fact covered in this video up to this point, every star, every galaxy, every red dwarf that will outlast everything else, every white dwarf, every black hole, belongs entirely to that smallest slice, the 5%. The other 95% of the universe, the part that will ultimately decide which of the three endings this video describes actually happens, is made of two things nobody has ever directly touched, measured, or captured, only inferred from the behavior of everything else around them. And just like dark matter over in the degenerate era, dark energy has never been directly detected either. Its existence is inferred entirely from its effects on the universe's expansion rate, not from any particle or signal anyone has ever actually captured. The scenario built into everything described tonight is called the Big Freeze, or heat death, a phrase with roots stretching back much further than modern cosmology, all the way to the mid-1800s and the birth of thermodynamics as a science. The whole idea traces back to engineers and physicists trying to understand steam engines. French physicist Sadi Carnot made the first real breakthrough in 1824, analyzing how efficiently an ideal engine could convert heat into work, though he was still working with an outdated idea of heat as a physical fluid. It took German physicist Rudolf Clausius, in 1850, to properly formulate what's now called the second law of thermodynamics. Heat does not spontaneously flow from a colder body to a hotter one without outside work being done to force it. Scottish physicist William Thomson, better known by his later title Lord Kelvin, worked out an equivalent version of the same law independently around the same time, in 1851. 15 years after his original 1850 paper, in 1865, Clausius went further and coined an entirely new word to describe this one-directional tendency toward disorder: entropy. That single concept, entropy always increasing in a closed system, is the direct ancestor of everything Adams and Laughlin describe happening across cosmological decades 10 through beyond 100. There's something worth pointing out about where this idea actually came from, because it's easy to assume a concept this vast, one that describes the ultimate fate of literally everything, must have started with someone staring up at the stars, thinking big, cosmic thoughts. It didn't. It came from 19th century engineers trying to figure out why steam engines wasted so much of their fuel as heat instead of useful motion, a thoroughly practical, industrial problem about pistons and boilers and coal. Nobody involved was thinking about the death of the universe. They were thinking about efficiency, about how much work you could squeeze out of a given amount of coal, and it just so happened that the mathematics they worked out to solve that narrow, practical problem turned out to apply, without modification, to absolutely everything in existence, all the way up to the largest possible system there is. Applied to the entire universe treated as one enormous closed system, the second law implies exactly the kind of ending this video has been building toward: an eventual state of maximum entropy, where every usable difference in energy has been evened out completely, and nothing anywhere can do any further work at all. If dark energy behaves as a true, unchanging cosmological constant, a fixed pressure baked permanently into the fabric of space itself, expansion never stops, never reverses, and the universe simply grows colder and more diffuse forever. eventually reaching exactly that state. Before dark energy was discovered, many cosmologists actually expected the opposite outcome, something called the Big Crunch, in which gravity eventually wins the tug-of-war against expansion, halts it, and pulls everything back together into a hot, dense state, resembling a mirror image of the Big Bang, a symmetric ending to match the symmetric beginning. The discovery that expansion is accelerating, not slowing, effectively knocked the Big Crunch out of favor as the most likely outcome, though scientists are careful to note it hasn't technically been ruled out entirely, given how comparatively short our observational window still is, a matter of decades set against billions of years. There's a third, more violent possibility too, called the Big Rip, which requires dark energy to actually strengthen over time rather than stay constant, something physicists call phantom dark energy. In that scenario, cosmic acceleration eventually grows strong enough to overpower gravity itself, then the electromagnetic force, then even the strong nuclear force holding atomic nuclei together, tearing apart galaxies, then stars and planets, and finally atoms themselves, at one specific, calculable moment in the future, a definite date circled on an otherwise indefinite calendar. It's worth noticing how differently that scenario would unfold compared to everything else this video has walked through so far. Heat death is patient. It's the slow, orderly running down of a universe that keeps expanding at a manageable, roughly steady pace, giving red dwarfs their 10 trillion years, giving white dwarfs their proton decay timescale, giving black holes their unfathomable evaporation windows. A Big Rip throws all of that pacing out. Instead of a graceful fade stretched across 100 cosmological decades, everything, galaxies, stars, planets, atoms, would be torn apart in a comparatively sudden, violent final stretch. The difference between a candle burning down over hours and a candle being yanked apart by a widening crack running straight through it. Current measurements place dark energy's behavior very close to that constant value, which is why the heat death scenario remains the leading picture. But ongoing missions like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope are actively testing whether dark energy might be quietly evolving after all, gathering new data as you watch this. Some early results have hinted that it might not be perfectly constant, though the evidence so far isn't considered conclusive by the scientists analyzing it. There's something worth appreciating about the fact that this specific question, arguably the single biggest variable determining how this entire video's ending actually plays out, is being actively narrowed down right now by real telescopes, collecting real data on a schedule measured in years rather than cosmological decades. Everything else in this video describes physics locked in place, unfolding on its own fixed timeline no matter what anyone does. This one detail is different. It's a live, ongoing measurement, and the answer, whichever way it eventually lands, hasn't finished being written yet. So keep in mind, everything in this video describes the leading theory, not a locked-in certainty, and the instruments capable of narrowing that uncertainty down further are working on the problem right now, in the present day, while you're watching this, adding new data points to a question that's still genuinely open. Assuming heat death is indeed how this plays out, and it currently is the best supported outcome by a comfortable margin, once every black hole in the universe, from the smallest to the most supermassive, has finally completed its evaporation, somewhere past the 100th cosmological decade, the universe crosses into its last known chapter, what Adams and Laughlin call the Dark Era. By this point, there is no matter left in any form anyone would recognize, none whatsoever. No stars, no planets, no white dwarfs, no neutron stars, no black holes. What remains is an extraordinarily thin, cold scattering of photons, the particles of light, along with leptons like electrons and positrons, and gravitons, drifting through a universe that has expanded so much, stretched so thin, that these particles rarely, if ever, encounter one another again, across unimaginable stretches of otherwise empty space. It is, by any reasonable definition, the true end of structure in the cosmos, the final, permanent state that heat death describes, the last chapter in a book that started with a hot, dense point smaller than an atom, and the same physical principle Clausius named entropy back in 1865, playing out to its absolute, ultimate conclusion. Even here, right at the furthest edge of what physicists feel comfortable calculating, physicist Freeman Dyson tried to work out, in careful mathematical detail, whether anything resembling life or thought could possibly continue past this point, and his answer, published in a 1979 paper called Time Without End, is worth walking through directly rather than just gesturing at. Dyson proposed that a hypothetical form of intelligent life, adapted to function at extremely low temperatures, could survive the dark era using a strategy that basically amounts to extreme, patient hibernation. The idea works like this: store a finite amount of energy, then spend half of it powering a single burst of activity or thought. Once that half is used up, shut down completely, into a state that consumes no energy at all, and simply wait for the universe to cool further. Once it has, spend half of what's left, a quarter of the original total, on another burst of activity. Then power down again, and wait even longer than before. Repeat that pattern forever. Half the remaining energy, then hibernate, then half again, then hibernate longer still. Because the cost of a single thought in Dyson's proposed scaling law drops as the surrounding temperature drops. Each burst of activity can stretch out longer and longer, using proportionally less and less energy, and Dyson's mathematics show that this process could, in principle, repeat an infinite number of times using only a finite total energy budget, meaning a being following this strategy could experience an effectively endless, unbounded subjective lifetime even as the universe around it grows colder and darker forever. It's a genuinely elegant piece of physics, and it's worth being honest about where it runs into trouble too. Dyson's original 1979 calculation assumed the universe would go on cooling indefinitely, without any lower limit, forever approaching but never quite reaching absolute zero. There's something worth pausing on in that hibernation scheme itself, regardless of whether the underlying cosmology holds up. It describes existence stretched out so thin that periods of actual thought or activity become vanishingly brief flickers, surrounded by unimaginably long stretches of complete dormancy, waiting. A being living out Dyson's proposed strategy wouldn't experience most of its own existence as anything at all. It would experience a handful of active moments, each one longer, subjectively, than the last, separated by silences that dwarf everything else in this video combined, over and over, forever. The discovery of dark energy in 1998, 2 decades after Dyson's paper, complicates that assumption. In a universe where expansion is accelerating the way ours appears to be, there turns out to be an actual flaw to how cold any observer can ever get, a specific minimum temperature called the Gibbons-Hawking temperature, caused by faint thermal radiation generated by the universe's own cosmological horizon, the boundary beyond which nothing can ever causally affect us again. If that flaw is real, Dyson's original infinite hibernation scheme, exactly as he first proposed it, doesn't survive contact with modern cosmology, since the whole strategy depends on the surrounding temperature being able to drop without limit. Physicists have proposed various updates and workarounds since, but the clean, elegant version from 1979 needs an asterisk attached to it today, a reminder that even the most rigorous speculation about the far future has to keep getting checked against whatever cosmology discovers next. Adams and Laughlin, writing 2 decades after Dyson, cite this same broad idea, the notion, credited to physicist Freeman Dyson, that the pace of metabolism, and by extension, the pace of anything resembling thought or consciousness, should scale directly with temperature. In an ever-cooling, ever-darkening universe, that raises a genuinely strange possibility worth sitting with. Some form of impossibly slow, impossibly patient structured process might still exist out there in the dark era, thinking one single thought across spans of time that dwarf everything already covered in this video many times over. They also touch on the far more speculative idea that entirely new universes might somehow arise out of these conditions, a kind of cosmic rebirth at the very edge of theoretical possibility. Other physicists and futurists have floated even more speculative escape routes worth a brief mention. Inventor and futurist Ray Kurzweil has suggested a sufficiently advanced form of post-human or artificial intelligence might eventually gain enough control over the physical universe to avoid heat death altogether, and some theorists have speculated that intelligence might attempt to seed an entirely new baby universe through a hypothetical wormhole as a kind of last resort survival strategy for information, or life itself, if not for any individual being. None of this is presented as established science, and it shouldn't be treated that way here either. It's the far edge of theoretical speculation, offered honestly as speculation, sitting right at the boundary where physics starts to blur into philosophy, the point where equations run out and imagination has to take over instead. There's something worth noticing about where all of this speculation actually sits inside the larger timeline of this video, because it's easy to lose track of it by this point. Everything Dyson, Adams, Laughlin, Kurzweil, and every other physicist mentioned in the last few minutes have proposed happens after the 100th cosmological decade, after every star, every white dwarf, every neutron star, and every black hole, down to the smallest one, has already finished its part of the story. None of these are proposals about how to prevent any of the earlier stages described in this video. Red dwarfs still fade out around 100 trillion years, regardless of what any future civilization does. Proton decay, if it happens at all, still runs its course. Black holes still evaporate on their own impossibly long schedules. The Dyson hibernation scheme, and its various proposed successors, aren't attempts to stop the universe from cooling. They're attempts to answer a much narrower, much stranger question. Assuming all of that happens exactly the way current physics says it will, is there anything at all that could still be happening, still thinking, still experiencing time, on the far side of it? Nobody currently knows the answer. That's precisely why it's speculation, and not a fifth chapter, alongside the stelliferous, degenerate, black hole, and dark eras. But it's a genuinely different kind of not knowing than most of the uncertainty in this video, because it isn't about which numbers are correct. It's about whether the story described so far is a complete ending, or just the last part anyone currently has the physics to describe. So that's the actual shape of the ending, laid out the way current theoretical physics understands it, built from the ground up, starting with the very first light of the universe, still detectable today as a faint microwave hum discovered almost by accident by two radio astronomers cleaning pigeon droppings out of an antenna, through the very first stars flickering on somewhere between 100 million and 400 million years after the Big Bang, running through the sheer scale of what exists right now, something on the order of 2 trillion galaxies, and anywhere from a couple sextillion to over a septillion stars, depending on the method used to count them, catalogued and classified using a diagram two astronomers built independently more than a century ago. All of it organized into superclusters, like our own Laniakea, 500 million light-years wide, and still just one small corner of everything, past the personal, much sooner deadline waiting for our own sun, a deadline that ends with a slow crystallization process only directly confirmed by a spacecraft in 2019, past a nearby giant star already flickering toward its own explosive end right now, past a real, named 7-planet system that will still be shining long after everything else in this story has gone dark, through a 400-year-old puzzle about why the night sky is dark at all, and its stranger cousin, a puzzle about why the galaxy seems so empty of anyone else, out through the slow dimming of every remaining star in the universe, the strange statistical case that life itself may be arriving early rather than on time, past a galactic collision whose predicted gravitational fireworks rest on physics, directly confirmed in a laboratory less than a decade ago, past our own galaxy's black hole, already photographed, already patient, the quiet decay of every scrap of ordinary matter, a decay dependent on a mysterious substance nobody has ever directly detected, past the ghostly, still-spinning remnants that once were stars, discovered by a graduate student who noticed something odd in a stack of paper, the patient evaporation of every black hole down to the very last one, and finally settling into a cold, structureless dark that, as far as anyone can currently tell, simply goes on forever without end. The ultimate expression of a single idea a 19th-century physicist first put into words while trying to understand steam engines, and possibly, if one physicist's careful 1979 mathematics still holds up, not entirely without the faint, patient possibility of thought continuing somewhere inside it. It isn't a single dramatic event, it's a cascade, one stage quietly giving way to the next, across timescales that stack on top of each other until the numbers themselves stop feeling real, stop feeling like they describe anything a human mind can actually hold on to. It's genuinely strange to sit with the idea that the universe as it exists right now, full of galaxies and starlight and a night sky dark enough to still puzzle astronomers centuries after Kepler first noticed the problem, and quiet enough to still puzzle physicists decades after Fermi first noticed a different kind of silence, is really just one early, brief, and unusually bright chapter in a story that keeps going for numbers of years that don't have any everyday comparison left to reach for. Numbers that stop meaning anything the moment you try to actually picture them. It's the kind of fact that doesn't really change anything about how anyone actually lives, and yet it's hard to look up at a clear night sky the same way again once you know it. Every point of light up there is mid-story, not anywhere near the beginning, and nowhere near the end either. Caught in exactly the same brief, bright window this entire video has been describing from the very start. Every star anyone has ever looked up at is going to go through some version of what we've just walked through. So is every star that hasn't been born yet, every star still waiting inside some cloud of gas somewhere in some galaxy, not yet ignited. So will our own sun, on a timeline measured in billions rather than trillions, which almost makes it feel close by comparison, practically next door on this kind of scale, practically tomorrow. It's worth ending on that thought rather than rushing past it. Everything described in this video, from the first flicker of starlight to the last fading photon, applies to every star equally, without exception, including the one currently rising or setting somewhere outside your window right now. None of that makes tonight's sky any less worth looking at. If anything, it does the opposite. Every fact in this video, the dark matter nobody's ever caught, the proton decay nobody's ever witnessed, the Hawking radiation too faint for any instrument humanity has built to measure, the crystallizing white dwarfs only confirmed 6 years ago, the companion star hiding next to Betelgeuse only found last year, is a reminder that this entire account, as long and as far-reaching as it's been, is still being actively written by people working right now, with instruments that keep getting better, asking the same basic question in more and more precise ways, the same handful of questions humans have been quietly asking every clear night for as long as anyone has bothered looking up. The universe isn't a finished story being read back to us. It's an ongoing one, and the ending, if it even is an ending, is still being calculated, decade by decade, cosmological decade by cosmological decade, by people looking up at exactly the same sky you can go outside and look up at tonight, asking the same handful of questions, with better tools than the generation before them had, one clear night after another. That's the actual scale of the story astrophysics tells about the future, built not on guesswork, but on the same physics that explains the stars shining above us tonight, extended forward, as far and as honestly as current science can take it, one careful calculation at a time, from a graduate student's stack of paper, to a spacecraft's precision map of the galaxy, to a photograph of a shadow 27,000 light-years away. Each one a small, human-sized piece of evidence, stitched into a story that outlasts every person who will ever help tell it.